So good afternoon, everybody. Welcome to this webinar about AI-based intelligence and reconfigurable manufacturing systems. So you will learn in this webinar how artificial intelligence can be used to make easy reconfigurable machines, AGVs, in production floor to deal with variable production missions and variable products. So this webinar is organized in the framework of the AI Flanders Research Program. On behalf of the program coordinator, who cannot make it today, I am pleased to give an introduction to the AI research program and moderate this session. So my name is Bey-Temsamani Abdel. I am project manager and researcher in Flanders Make, mainly active in the Industry 4.0 technologies, where artificial intelligence is becoming an important technology in the framework of the digital transformation wave of industrial and manufacturing systems. So the agenda in the webinar of this webinar contains 2 research and 1 industrial presentation, followed up by Q&A session. So if you have a question, please raise them in the Q&A session at the end of this webinar. So I wish you all a constructive session. So the first presentation that will be given is to introduce the Flanders AI research program, and we will focus more into AI for Industry 4.0. So Flanders annually invests, or the Flemish government annually invests 32 million euros in a policy plan for artificial intelligence with a focus on research, practical application, and guidance in the field of training, awareness raising, and ethical questions. The AI research program where this webinar fits in focuses on leading edges AI research and pioneering proof of concepts for healthcare, Industry 4.0, government, and their citizens. So the program involves many partners, representative for research in Flanders, and including 5 universities, namely KULeuven, University of Antwerp, Ghent University, University of Hasselt, and Free University of Brussels. It's also involved 5 research centers, IMEC, Flanders Make, Series, VIB, and VITO. So next to these organizations, federations and network organizations such as Agoria and VOCA is set up to create links with industry. Next, also to close cooperation with other pillars in the overall AI Flanders program, like the KDM, the FIA, VLAIO, for the public funded R&D projects. The research in AI Flanders concentrates on complex and generic questions for which there is no off-the-shelf solution. These research challenges came out of an analysis of the needs within different applications where complex decisions need to be taken, such as safety-critical industrial systems or healthcare systems. On the other side, intelligent distributed systems become more and more available in smart manufacturing, smart cities, and other applications. Edge AI with energy efficiency and low latency is an important research for this application. The next level is to move from passive distributed systems to cooperative systems that require another level of AI management. So all these research topics are down where human remain centric in the loop, resulting to augmented intelligence as expressed by our Prime Minister in the AI Week event. So this results in research to guarantee seamless cooperation between machine and human, as we will see today. So demonstrators will also illustrate the applicability of the research. They also have the goals to inspire companies and organizations to regularly test and validate the research against the needs to reveal new generic research topics. This long-term interactive cycle forms a kind of a flywheel for innovation. The ambition is that companies, of course, and organizations take up the research results and apply them in their specific context. So we will focus more into the Industry 4.0 in this session. And concretely in the AI research program, there are 4 research directions referred in the program as grand challenges. So the first one, called AI-driven data science, target to make data science hybrid, automated, trusted, and actionable. The second one is about the edge AI, focuses on the real-time and power-efficient AI in the edge. The third one is about collaborative AI research, where multi-agents interact autonomously with each other to make complex decisions. The fourth is about human-like AI research, where machine and human communicate together in a seamless way. We will see in this session how some of these techniques are applied to application toward Industry 4.0. By the way, this Industry 4.0, namely also the fourth industrial revolution, is driven by data to create intelligent systems. Some examples cover transition from, for instance, paper to digital instruction, doing automation from robots to cobots, corrective to predictive maintenance or performance prediction, as well as from manual to autonomous systems. So in all these examples, it's very clear that artificial intelligence can play a major role to make these systems more intelligent. As you can see, for instance, in the digitalization process, AI can transform all this digital data into smart instructions from the operators or the machine. For the cobot's interaction with the human, smooth cooperation can be guaranteed by adding AI to whatever sensors that are equipped in these systems in order to make a more seamless decisions between machine and human. The same applies when you are doing predictive maintenance or predictive performance of your assets. AI can also play a role to predict failures and optimize the performance. Last but not least, AI can also play a major role in autonomous systems, as we will see today, to make, for instance, these AGVs more instructable in a kind of smooth way. So in the AI research program, we would like really to demonstrate these capabilities in the Industry 4.0 framework. And that is the reason why we are trying to demonstrate what we call the factory of the future. So in this factory, machines, robots, and human cooperate to efficiently produce custom parts. So AGVs, for instance, they are deployed to perform different logistic operations and can be easily reconfigured to perform different missions. Machines are learning from each other to perform different tasks and include self-assessment system to check their performances and conditions, but also connected to the cloud to collaborate with other production systems and optimize production processes. So all these cases are part of this research program we are conducting with different partners. So we are really working out a very concrete cases that we are able to demonstrate to the industrial audience, but also to the other, let's say, people or other applications, how artificial intelligence can create or can leverage the systems and bring them to the next level or the next generation that allows smart factories, smart manufacturing, intelligence manufacturing, and so on. So that's exactly in this presentation or in this webinar today, we would like to focus in 2 applications out of these applications. So the robust and instructable AGVs and the control of machine park. So that's exactly what you will see in the coming presentations today. So that's it from my side. So now I would like to introduce the next presentation, which is going to be about instructable AGVs, I assume, so given by Maybe you can share already your screen.
Yes, it's happening. Thank you, Abdel.
Thank you.
So as Abdel mentioned, yeah, I'm going to talk about the AGV case.
So I will first introduce you, Quinten. So
Yes.
also together with a colleague that he will give the presentation with you. So the presentation is going to be about controlling an industrial vehicle through speech with minimal custom data. So this presentation is going to be given by a duo. So Quinten Lauwers is an engineer in Flanders Make. He has a master's degree in computer science with the option of artificial intelligence. He has been working on autonomous vehicles and their perception systems since his graduation. On the other side, we will also have in this speech Hugo van Hamme. Hugo van Hamme got his PhD degree from the Vrije Universities of Brussels in '92. He has been holding different positions as senior research and senior director of research at Lernout and HOSPI. In 2002, he joined KULeuven as a professor in speech processing, and his research interest covers different topics like speech recognition, acoustic source separation, etc. He also been behind the startup called Flanders AI that was created based on his research results. So then now please go ahead, Quinten and Hugo, in the next presentation.
Thank you, Abdel. So as mentioned, I'll be talking about controlling an industrial vehicle through speech with minimal custom data. This talk first, let's maybe give a bit of an overview. I'll start a bit with the motivation. Why should you care about controlling an industrial vehicle through speech? Then I'll talk about the methods we used to implement some demonstrators. Then some common problems or some problems we encountered, which we think are quite common when implementing AI algorithms. And then finally, I'll end with a bit of an overview of the broader scope of what we're doing and what we're doing within the AI program. So first, let's start with a bit of motivation. Why should you care about controlling an industrial vehicle through speech? So one thing we noticed is that as AGVs get more and more capabilities, the complexity of the systems that control these AGVs also increases. And while this automation makes companies a lot more productive, it does also make manufacturing more rigid. It becomes more difficult and more difficult to easily reconfigure these systems. And let's start maybe with a concrete example. So let's say you have Dave. Dave works in a factory and he wants to move a pallet. The factory is quite far automated. There are mostly AGVs there. So the question then becomes, can he instruct one of these AGVs to just move the pallet for him? Or does he still need a forklift driver or drive the forklift himself? So there are multiple options here. For example, you could make the AGV instructable with some kind of user interface, which would probably take quite a bit of time for him to configure this AGV to move this pallet, to instruct it to that. Another possibility would be to keep one of these manual forklift driver, which would require him to have a license and to keep one person for this, or at least one regular forklift for these kinds of applications. So our idea then is to integrate a more intuitive control into this AGV, for example, using speech processing, which is also what we've done. So I'll talk a bit more about how we did that, the speech interface. So basically we are experimenting with more intuitive control of AGVs. We're looking at the advantages and different disadvantages of different approaches. For example, of commercial tools like Google Dialogflow or custom trained speech detection algorithms from the KULeuven. And we're actually going through the full process. So we go from gathering the data, configuring these possible networks, these systems, commercial systems like Dialogflow, selecting all the right parameters and actually implementing it and then testing it on a vehicle as well. So the first step in this process would be to gather the data, which already presents a challenge. For example, for speech data, typically, if you ask people to give the instructions for certain situations, they will not use the same commands that they would in real life. So to get around that, at Flanders Make, we created a simulator in which we gave people kind of problems to solve. So they had to move to a certain location or pick up a certain pallet, and then to do that by saying speech commands, which then allowed us to gather relevant data as if they were really controlling the vehicle in those situations, which creates quite a bit more relevant data. Like, for example, when things go wrong, people say, for example, or utter certain instructions at a completely different tempo than when you're just calm and explaining instructions step by step. From there on out, we're integrating it in the speech algorithms. We're training it with the algorithms from the KULeuven or in Dialogflow. At the same time, we're also working on perception. The focus will be slightly less on that in this talk, but we're also working on, for example, detecting pallets, those kinds of things, the vision systems. From there on out, we have an architecture that allows us to easily integrate these kinds of systems into the tractor. If we go a bit more into detail on this, in the next slide, you can see we have kind of a system where it allows us to plug in these modules, for example, with speech detection from Dialogflow or from custom trained natural language processing, which Hugo will talk a bit more about. But the same thing goes for perception, where we train existing neural network architectures, but where it's also possible to integrate custom neural network architectures, for which we're also collaborating with the KULeuven. And then from there on out, we do have a whole architecture to kind of keep things safe and easy to integrate and to make abstraction of a lot of the functions of, in this case, a tractor. So I'll maybe first start with a small demonstration of what this looks like with Dialogflow, which is a tool from Google that allows you to easily get one of these systems up and running. So it just allows you to specify a few example sentences, what kind of actions your vehicle can take, and then from there on out, it generates a speech detection algorithm. So that's the first thing that we did. I'll play this. So here I'll quickly pause. For example, one of the disadvantages of this Google Dialogflow is that it first uses speech to text and then tries to recognize your intent, or the action that you want to take from this transcribed command that you spoke. So here, I don't know if you can read it, but in the left bottom corner, you can first see that it, as intermediate transcription, recognizes me saying rechtdoor or straight ahead in English. But then the final transcription is kind of mangled here, which means it can't recognize that I said straight ahead, even though what I spoke and what's transcribed there is quite similar to the command for straight ahead. Right, so another few possible disadvantages of the system are in Dutch, it doesn't work as well as in English, this Dialogflow. And it also isn't great at detecting either local dialects or, for example, if you have jargon, so very specific words to your area of expertise. Because of this speech-to-text engine, if it doesn't really can recognize your words, then this will also fail. So then the more state-of-the-art solution that was developed by Hugo van Hamme we also integrated, and here you can see the results of that. So another advantage of these kinds of solutions are that it allows us to quickly reconfigure these systems. So this was a custom trained neural network, which has the advantage that it can run locally, first of all. So this was all done locally on the tractor, as opposed to Google Dialogflow, where every command was first sent to the Google servers. So if we show then the effects of being able to run it locally and having your own network, one of the things you can do is if it doesn't recognize a certain command, which I will show here, for example, the lifting wasn't trained properly or something went wrong there, it's easy to quickly retrain the network to recognize this command. And I'll also show that here. So this is the interface that allows you to quickly retrain this. And then here you're going to see that I'll select the correct interpretation of this command and then save the feedback. All right, and then I'll hand the word to Hugo, who will explain a bit more about his presentation. Hugo, I don't know if you have control. Yeah, okay. You're still muted, Hugo.
Yeah.
Sorry, I was waiting for the video to stop to take control. All right, good afternoon. So what I would like to do now is to point out a few fundamental differences between the traditional approach and the approach that we propose. So traditional, I mean the Google Dialogflow. So essentially what you want to do is to map some speech. I hope you see my cursor. Can anyone confirm that you see my cursor?
No, we cannot see your
Okay,
cursor.
then I will just describe where I'm pointing. To map the speech represented on the left side to an actual call to the programming interface of the machine on the right. So a call like slowly drive a little bit forward would have to be mapped onto a call to the API, which is composed of different of an actual function plus some arguments. So the traditional approach would be to map first the speech through an automatic speech recognizer, which is one of the things that Google just makes, onto a textual representation, which you see in the middle, and then have a so-called natural language understanding component, which maps that onto the API call. So the advantage of that is that you can leverage all of the experience that Google has in making automatic speech recognition engines to transform the speech into the text. Then you can you have some interface with where you can type in fields how particular words have to be interpreted in terms of the API call. And so that's the pro really of this advantage. But those pros are actually in some situation also cons for the approach. First of all, you make the cascade of two systems which are made independently. So as Quinten showed, if there is a speech recognition error, the natural language understanding unit will not really know what to do with that word, since it's never seen that erroneous word before. So you have an accumulation of errors. If one of the systems makes an error, you will have garbage at the output. Secondly is what you actually say or what you type when you're asked to give typical commands that you would say to the machine is actually different. So if you do recordings, if you observe humans performing this task, you will see a difference between what they type at some point in time and what they actually say even 5 minutes later, or in reality a few months later. Another point is non-natives, dialects, and speech disorders. Quinten was talking normal Dutch, but we all know there's quite some dialectal variation, and with non-natives, you cannot expect the pronunciation of all words to be standard, and also the automatic speech recognizer will typically fail on that sort of data. And then in this industrial context, like this palette will have to move objects which are specific for a particular company. How will you call that? How will you name those objects? That's and actions. That's also very specific to a particular company, to a particular setting. All that has to be done through typing. Then it's in the natural language understanding unit that you would have to figure out how to map that onto API calls. So that's that application-specific vocabulary is a problem. So our proposed approach is to map directly the speech into the API call via one integrated neural network. So the maybe I should mention also the way you then train it is to provide the system with some speech input and then some demonstration through some interface. It could be actually by observing you pushing the pedals on the tractor itself, or through an alternative interface as Quinten demonstrated. And then we learn this mapping directly from speech to this API call. So the pro is that the machine really learns how to what the speaking habits are of the users. It's okay for dialects and for non-native. It's even okay for speaking any other language, as long as you can have enough data to map to learn that mapping from the speech onto the API call. So the big disadvantage of this approach is that it does not work out of the box. So when Quinten went through his steps with Dialogflow, he had a working system. Here you have to provide a few demonstrations of what you mean with a particular command. We have a solution for that, and I will come back to that later during this presentation. The last slide I would like to, but I went to the completely wrong position in the slide deck. Let me go back. Here is where I have to be. The last point I would like to make before handing it back to Quinten is that we have an extensible approach here. And for the moment, it's about pushing pedals, turning the wheel, pushing knobs, and the commands that we can handle are fairly simple, and like turn a little bit to the left. That's the type of commands that you have seen. But the same concept can be applied and will be applied during this project to more advanced sensors, where you can do object recognition through a camera, for instance, and then you would be able to handle commands like and learn commands like drive to the yellow box right of the lamppost, or drive forward as far as you can. I mean, as far as you can would mean that the LiDAR sees that you're nearly at the object in front of you. So I will come back to the point of how we solve the problem of minimal data, which is the topic of this presentation, after some more comments from Quinten.
Thank you, Hugo. So indeed, as mentioned, these were all mentioned in the previous thing. To quickly reiterate, Google Dialogflow is very easy to set up. It's intuitive to use, easy to integrate, but as disadvantages, it doesn't have the best performance in languages other than English, does not handle privacy well, and possibly another disadvantage is that you both need an internet connection and that your data is in some way shared with Google. The advantages of the custom algorithm are that it can run offline and that has a better performance on the vehicle. I realize this is maybe a bit subjective, but when testing with it, I had a lot more confidence in the custom AI algorithm, because even a few percent better performance makes a huge difference when you're controlling such a large vehicle. And then the disadvantages are a bit that it requires some training, so it requires some relevant data, and that wasn't maybe mentioned so explicitly, but while the Google Dialogflow just keeps listening and interpreting commands, this one you kind of have to start, record your speech fragment, and then it will interpret it, which can be an advantage or a disadvantage, because you don't want it to interpret commands when you, for example, don't want to take manual control of the vehicle. As mentioned, this is just a part of a much larger system. So on the one hand, you have the speech interface. It will be linked to vision, as Hugo already brought up, to be able to do commands like pick up the red pallet or the pallet to the left or the right of a certain lamppost. On the other hand, we're also working together with the University of Antwerp to implement reinforcement learning and to look what the capabilities are there, which would allow us to handle more unexpected situation, changing environments, those kinds of situations. As to the linking with this perception system, for example, we trained an object detection algorithm that can mark these pallets already. This is the first version, but then the goal is to also link this to the speech interface. Now, both with this vision, this image recognition, and with the speech interface, there are some common problems that you will typically encounter when, in our case, training neural networks. And that is, let's focus on images maybe, because that's a bit easier to understand usually. When training a neural network, you typically need large amounts of data. For image recognition, that's typically in the order of like 10,000 annotated images, and it's very hard to cover all possible scenarios in your training data set. So we're also working on solutions for these kinds of situations. For example, in a project called Autorio, which is about picking up automatic pickup of trash. We're doing data augmentation with generative adversarial networks. So data augmentation is actually changing your input images slightly to kind of give more variation in your data set. Using generative adversarial networks, you can do something called style transfer. In this case, this was transferring images from between different weather conditions. So for example, on the left, you can see images that were taken with our system. And on the right, you can see then what one of our neural networks that we trained makes of it for when it would be in rainy conditions. So you can see that it even creates these reflections as if the ground is wet. Another technique that is typically used is pre-training of neural networks, where you use a similar, usually larger and publicly available data set to first train a neural network, and then you can possibly replace some layers in the neural network and then train again, but that's more of a fine-tuning step, because a lot of the information that the network learned will help to train your network faster. And I believe Hugo will also go a bit deeper into or explain how this works for the speech part that we just presented. You're muted again, Hugo.
So for the speech, again, what we want to do is to map the speech onto an API call, the speech on the left in the diagram on the top right. And so instead of, like Google does, going through a textual representation in the middle, we have some neural activation representation. Now, a lot of the data that we need goes into training a good encoder. So the encoder maps the speech onto the neural activation. Then the decoder maps the neural activation onto the actual API call for the vehicle. And so a lot of the data that we need is required for training a good encoder. Well, the idea is to use generic data for training the encoder. So we want to, that's the block you see below it, the second decoder that you see, which maps a neural activation onto text. So if you have a lot of training data, which is not application specific, which I can record on other applications, I will train the encoder actually using that data. So I can use my application specific data to only train the application-specific decoder from neural representations onto API calls. And in the bottom right, you see the huge impact that this makes. And so you have the line called language independent. There we learn everything from scratch, much like a baby does in reality. It learns to map speech onto a meaning, and in this case translated into an API call. And you see on the x-axis how much data you need and what accuracy you get on the y-axis. And so you see that with more data you get more accurate, but the number of utterances, training utterance that you need to get a particular accuracy is quite high. So if we then do the pre-training trick, you see that the accuracy goes up immensely. And if you, well, there's two variants. I will not go into the details of those two variants, but if you read the curve horizontally, if you see how much training data do I need on the x-axis to achieve a particular performance on the y-axis, then you see that you have an order of magnitude fewer data that is needed to train this application-specific mapping. And so it has a huge impact on the performance of the system, and especially on the perceived performance. As Quinten mentioned, a few percent can make a huge difference, but especially in how much training examples, how much demonstrations he has to give, it's an order of magnitude difference. I will hand it over to Quinten.
Thank you, Hugo. So finally, I'll quickly give an overview of what was presented. So we talked about intuitive control of an industrial vehicle. First, with speech, we talked about how it's difficult to capture the variation in input data. We had to write a simulator for that specifically. We talked about gathering this relevant training data. We explained some techniques both with vision and with speech about how you can try to minimize this training data that you need. And then for vision, there we also shown a trained network that used the pre-training trick, by the way. So that was trained with minimal data, the palette detection that you saw there. And then for future work, we're going to interface this with vision as well. And then in later steps, we're also working on advanced control through reinforcement learning. And then I had foreseen that there would be questions, but those will be kept by the end of the talks, I believe. So then I think this is it. Dries, I believe you might still have some questions for the audience then.
Okay, so thank you very much, Quinten and Hugo, for this nice presentation. I see here a polling question. I would indeed invite all the attendees to vote for the right answer, that we can also use this information in the feedback session at the end. So indeed, about the questions, if there are any questions or comments, please also put them in the chat, that we can collect them by the end of in the Q&A session and then discuss them at that time. Okay, maybe giving few seconds to attendees to vote for a second polling question. Okay, so I would like now to invite our, let's say, guest speaker, who is Patrick Puissant from Picanol. He will give a presentation on testimonial on challenges Picanol faces with data for similar machines. So, a short introduction to Patrick. So Patrick Puissant graduated in '94 at the Ghent University with a master's degree in electromechanical engineering. He works a few years as a researcher at the Department of Textiles at Ghent University and joined Picanol in 1998. So, and he's working now for more than 20 years in the R&D department of Picanol. He's responsible for the development of several control algorithms in order to save air consumption, optimizing the weaving speed of air-jet looms. In recent years, he is focusing more toward big data and industrial IoT. So Patrick, please go ahead with your presentation.
Okay, thank you, Abdel. Indeed, I was asked to give a testimonial on the challenges that we encounter with data coming from similar machines. So maybe a short overview of this presentation. I would like to say a few words about Picanol. Then I would also like to give a short introduction on weaving and the challenges that occur during weaving in general. I will say a few words about the availability of machine data. We'll also try to explain why should we look for data coming from similar machines weaving similar styles. And in general, I will also give some specific challenges that we encounter in the data. So maybe first short introduction about Picanol. Picanol is a part of the Picanol Group. Picanol Group is active worldwide in fields of mechanical engineering, agriculture, water management, and so on. We have facilities in more than 25 countries, more than 7,000 employees. But for the weaving machines, Picanol is active in also more than 100 countries. Currently, about 2,600 weaving mills are using Picanol looms. And Picanol has manufactured already more than 375,000 weaving machines that were installed worldwide. Picanol weaving machines are used for quite some applications. So we use weaving machines for general textile applications, such as jeans fabrics, shirting fabrics. Also for household and interior applications, Picanol weaving machines are used. Then we think about curtains, bed sheetings, all kind of terry fabrics. But Picanol machines are also used for niche applications, such as technical textiles, medical textiles, parachutes are an example of this. So our machines are producing sometimes very large volumes, like you see here, an example, denim fabrics are woven in very high quantities. And also for very specific technical applications, our machines are used. So there's quite a big range in applications. Our products, you can divide our products into two types of weaving machines. We have on the one hand Raper machines, like you see here, Optimax, Terimax, and so on. And on the other hand, we have also airjet machines. These machines can be divided into two categories. The high-end machines, these are produced here in Ypres. And besides these, we have also what we call machines for the mid-end market segments, and these are produced in China. A typical view on a weaving shed. So in a weaving shed, you will typically see a set of machines that are producing similar fabric styles. So like you can see in this movie, you have a few rows of weaving machines. You see one operator here, and these machines are producing almost the same type of fabrics. So that's what we can see as a typical example for a weaving mill. Okay. So something about the targets in weaving in general. So, of course, everyone wants to achieve the highest possible production output. This means that machine speed should be set as high as possible. Actually, we achieve industrial speeds of 1000 RPM and even higher. The number of stops should be, of course, as low as possible. And in our weaving mills, sometimes we get stop levels below 1 stop per 100,000 picks woven. This means that efficiencies should reach up to 99%. Of course, quality defects are not allowed, and a typical figure for us is that number of quality defects should be lower than 10 defects per 100 meters of fabric woven. And knowing that 100 meters of fabric means from 100,000 picks to 500,000 picks, this means that the number of defects that are allowed is very, very low. Of course, everyone wants the lowest energy consumption. This means lowest electrical energy for mechanical driving, but also the compressed air, the amount of compressed air should be as low as possible, and that is important for air-jet machines. One wants to achieve this with low-cost yarn material, and low-cost yarn material means that sometimes the quality of the yarn is not so optimal. And as we all know, the environment is challenging in our sector. This means that order lengths are becoming shorter and shorter. So this means more style changes are needed. And we can see that skilled labor forces are becoming less available. But maybe a few words about weaving now. So in order to get a fabric, one needs two sets of yarns. We have the warp yarns in this direction, and we have the weft-in yarn. And weaving means that a filling yarn is inserted between two layers of warp yarns. In order to get these two layers of warp yarns, the warp yarns are entered in heddles, and these heddles are moved up and down or these heddles are arranged in shafts, and these shafts are moving up and down. So that's one of the main motions in a weaving machine. You have this up and going up and down movement of the shafts. Besides this, you have also the sleigh movement. This sleigh movement will move the reed in order to push the yarn that is inserted against the cloth fell. Then, of course, we have the let-off movement in order to let off the warp yarns and to wind up the fabric that is produced. Of course, the insertion of the filling yarn is also one of the main motions. And weaving is then the interaction of all these different processes into one machine. Then also a few more words on the air-jet in weft insertion process. From data perspective, this is the most digitized yarn insertion process. And in air-jet weaving, the yarn is unwound from a bobbin, is prepared on a pre-winder, and is released from this pre-winder and is accelerated via a set of what we call main nozzles. So these nozzles are accelerating the yarn, and this yarn is then supported by relay nozzles from the left-hand side to the right-hand side. A few detectors are available on this type of machine. We have a filling detector that is detecting the arrival of the yarn. For instance, with this technique, we can achieve yarn speeds of up to 100 meters per second. Acceleration of the weft yarn is done in sometimes less than 5 milliseconds. So it takes only a few milliseconds to achieve this speed of 100 meters per second. The complete insertion process, so from start to the end of the weft insertion, it takes only about 25 milliseconds to complete this process. And in order to get everything controlled, you need to set quite some valve timings, pressures, in order to get the right air pressure in main nozzles and relay nozzles and so on. At the end of the insertion process, the yarn is also slowed down via a brake system. And these settings of pressures and valve timings have to be set for different channels. So this means that sometimes you end up with more than 1,000 settings to control such a weaving process. So as mentioned, challenges during optimization, target is to get the lowest possible stop level. Stop levels of 1 stop per 100,000 picks. This means that you need a lot of time to evaluate a change. So with these stop levels, we have only a few stops a day. So if one is trying to optimize the process, the settings, for instance, it will take easily a few days to evaluate the changes. Besides this, we know that also many stops that are occurring on the machine can be related to external reasons, such as the quality of the yarn, for instance. Of course, no quality defects are allowed, but on the other hand, and that's a big challenge, there is no direct information on the quality that is woven on the loom. So if a defect is occurring, it can happen that you don't see it in the data, you don't see it in the signals. Besides this, quality checks are also done after weaving. These quality checks are normally not done during the weaving process. So if you could get the feedback, you can only get this feedback later on. And also this information is nowadays not available on the loom. So the approach that is currently mostly done is rather via troubleshooting and trial and error. So one is trying to increase the speed or is lowering the air consumption. And at a certain moment when stops occur or when fabric defects occur, then one will try to change one or more settings and see what, and we'll see if it's better or not. Another difficulty here is that the link between the type of defect and the measure to be taken is not always so clear. So for a certain quality defects, sometimes there are many ways available to reduce this quality defect. Then also we have the aspect of style change. So with a style change, it means that other yarns are to be woven on the machine. So this also means that optimal settings can be different. Of course, experience helps here a lot in order to get the good settings on the machine. So what we can do is store good settings from the past and introduce them in the machine when we have to start a certain style that was woven in the past. But of course, what also can help is look how similar machines are weaving a similar fabric style. In order to detect similar machines, that's not that difficult. We know the machine execution, so that's rather straightforward. But in order to detect if a weaving machine is weaving a similar style, that's a bit more difficult. We can enter the specifications of the yarns that are woven, but we see in practice that it's sometimes risky to rely on this type of information that is entered in the machine. So that's not always correctly. And even when the operator has set this correctly, it's not sure that the same yarn material will behave in the same way. And if it's not behaving in the same way, then it means that other settings can be optimal. So what is better in this case is try to find machines weaving yarns with the same behavior. But that's quite a challenge. How can we get access to the data? So one machine cannot see the data from other machines, or not for the time being. How to assess this data, how to compare this data is a challenge. In general, how to know what a machine is weaving is quite a challenge. So what is available nowadays? A short overview. Production data, that's for sure available. That's since long time available in the machine. So this means the number of picks, the fabric length that is woven, that is available. So all kind of production timing, start, stop information about the stop type, that is available. What is also available, that is all kind of settings data. All the electronic settings are of course available. As explained, also some fabric style properties, construction details are available. On the other hand, yarn type and count, yarn other properties can be entered in the machine, but it's sometimes difficult to rely on this information. Other settings data that is of course available is all the valve timings, air tank pressures, and so on and so on. There is also some sensor data available. For instance, for the warp tension, we measured warp tension. This tension is available in the machine. Also all kind of insertion data, especially related to edge weaving, like yarn arrival timings and windings data, that is also available. Then some controller data, some controllers that are, for instance, regulating the air pressure in order to get a arrival time of the yarn at the right level. These data is also available. But this data is only stored in a machine and is stored for a certain amount of time. For instance, for the production data, we have this data available for the last 14 days. Other data points are available at different time stamps. So a short overview of all data challenges we encounter is, as I said, the data is stored inside the machine and is stored there for a while only. So this goes from a few minutes for some data points to a few weeks, like for instance for the production data. So different period for different items. Historically, the data is available in the machine, but you have to extract the data in a manual way. Luckily, we are trying and getting more and more machines connected to our Picanol cloud system. Today, that is for a limited number of machines at a limited number of customers, but this number is increased and can be expected that the number of connected machines will increase in the near future also. So from this point of view, the amount of data will increase, so more and more data will become available. Nowadays, when we have machines connected to our cloud system, the data is sent in batches. So a few times a day, data is sent, but we are moving towards streaming of data, and this trend will also become more and more important. However, we are receiving more and more data, but we have seen that this data needs to be curated. So we need to use and put uniform timestamps. We have to remove overlapping data. Filtering, remove incorrect data is important. So in general, I have to admit that this is an underestimated effort. So more data is available, but it takes some time and effort to get the data in a curated way. And then, as mentioned, there is a lack of knowledge on what is woven. Style data, as mentioned, is not always reliable. How to solve this? We believe that detecting yarn behavior can help us. So that will help us to indicate from what machines can we take over, settings for instance. We are thinking about adapting controllers based on this yarn behavior. So learning from machines with similar yarn behavior, we believe that this can help us in the future, but knowing all these data challenges, yeah, we are also convinced that it will need quite some effort to achieve good results. And how to do this, yeah, we are wondering and asking ourselves if AI techniques can help us in this matter. So I'm about the end of my presentation. I will refer for the questions to the Q&A session afterwards. So that's it for my presentation.
Okay, thank you very much, Patrick, for this nice testimonial about the challenges for data between machines, which is indeed a relevant topic, I think, for many industrial partners. So, of course, if you have questions to Patrick, please put it in the chat or raise it in the Q&A session. But also, if you have challenges for your industrial applications, please also share them, that we can also discuss them in our Q&A or give you maybe feedback after this webinar. So as we are speaking about machine-to-machine, let's say data management, I would like now to invite the next speakers who are going to give presentation related to efficient machine control exploiting data from similar machines. So this presentation is also going to be given by a duo, so Bruno Depraetere from Flanders Make and Jan Helsen from the VUB. Short intro, first of all, to Bruno. So Bruno Depraetere is a research engineer at Flanders Make. He received his PhD degree in engineering science from KULeuven in 2012. He researched advanced control method for industrial applications, both during his PhD, but also in Flanders Make, where he continued working on this topic to support wide range of Flemish companies. Jan Helsen is a professor at VUB in the Acoustics and Vibration Research Group. Jan got his PhD in mechanical engineering at KULeuven, and he performed research at different institutes, amongst others at MIT in USA. He coordinates a research team focused on condition monitoring and AI-based control. So his team has several national and international projects running in that field. He is also co-principal investigator in the Impulse program or the AI Flanders research program. And he is also chair in the drivetrain committee of AWI and member of IEA task on digitalization. So I would like to welcome both of you to give the next presentation.
Okay, thanks, Abdel. Good afternoon, everybody. So as Abdel explained, we'll give a talk about improving machine control, trying to exploit data from similar machines. We'll first start with a bit of an introduction. I'll try to link this also to the slides shown previously by Patrick from Picanol, highlighting a little bit of the same problem that we want to tackle, albeit on a somewhat simplified subcase of a full weaving loom, which I'll explain later, which is a bar linkage setup. Then I'll go a bit into the methods that you want to use to improve controller tuning, which we call hot starting. Also, Jan will there explain a bit of what methodology that we want to use. And then we'll show some demonstration videos of the hot starting in action, so there will be some results shown as well. So first of all, as Patrick already mentioned, there is often a need for controllers to work in many different conditions or on many different machines. Often needed to retune controllers to make them more performant. Can be due to different weaving speeds, different fabrics. Can also just be different operating conditions. It could also be starting up of new machines where you have to tune a new controller or tune a full new system to make it operational like the existing ones. This is true for many applications, but especially also for Picanol, with many weaving looms, as Patrick showed and explained, of which many of them are similar, and also many conditions. So I think it's not maybe that clear how many there are, but there can be millions of different settings or different conditions in which systems have to be tuned. if you can take all possible combinations. Again, holds for Picanol, but also for many other companies. So retuning all these controllers or retuning controllers for all these settings is of course not easy. It's not always automatic. It will take a lot of time, often of experienced personnel, which is something you don't always want to spend. As a consequence, this step is often skipped. So we often have, let's say, one controller or a few controllers that have to hold for all possible conditions. And due to the variety of conditions, this leads to conservative controllers. Again, referring to Picanol, most controllers that are tuned manually, machine by machine. There are, of course, experts like these operators that do tune and they have a knowledge in the back of their mind on how they tuned other machines, but there's no systematic procedure for reusing these past controller settings. As a consequence, there is need of a team of actual experts, so difficult to get these people, a lack of these people, and even then they don't always retune, or they're not always able to retune. So many of these conditions where they would actually benefit from retuning are not actually tackled nor exploited. So in this talk, the key idea is then, is it possible to automate this or improve this, this problem by using data from similar conditions or similar machines? So somewhat shown graphically at the bottom. So you have a database with many machines or conditions, each of them with a controller, ideally good controllers, bad controllers, maybe even the tuning process. And then can we, when we want to start a new task or a new system, can we use a kind of method for making the tuning of this new controller a lot more efficient than if you would normally do it? And given the scope of the webinar, we will focus on AI methods to do so. We will do so for a subset of a real Picanol machine. So a full machine has many subsystems and very complicated. We'll look at the part that's driving the frames that go up and down. So here you got motors, electromotors that rotate, and they drive through a crankshaft mechanism and a few bars, these frames to go up and down. So essentially, the basic motion is a rotation through a crankshaft and bar linkage to a slider, to a frame that moves up and down. We've taken built setup that's somewhat simplified, but has more or less the same essential components. This would be a very quick video, but a slow motion animation. So we have a system that makes a revolution and drives a slider left and right, which is very similar to the frame of a loom moving up and down, only in this case it's left to right. And this is very typical motion in the weaving loom, but also, for example, for motors, compressors, pumps. So this is not something only relevant for weaving looms, but it's much more a universal topic. Yeah. Okay. Like a loom, the frames move up and down, so we want to define a similar task for our bar linkage setup. So the frame, in this case, like the dashed lines, it moves from position 0 up and down again. So we will make our slider move back and forth, which is displacement. This is horizontal instead of vertical. And to then emulate a wide variety of tasks the weaving loom has to do, we will define different sets of constraints. So, for example, these gray areas, they define the motion that needs to be done. So for the weaving loom, this would be the left one. The left one would be defined by this dark gray bounding box. The frame has to be outside of this box at all times, so it has to very quickly move up and then very quickly move down. The light gray one would be much more smooth, so we can have much lower decelerations and accelerations. And then the goal that we will tackle for our bar linkages is to make the frame, or in this case the linkage, move, stay outside of this bound at all times while minimizing the energy. So we'll define different sets of these bounds to have different tasks that need to be performed. So this is an attempt of emulating the wide variety of tasks in a real weaving loom on the bar linkage setup. And then, of course, yeah, real weaving loom, there are many varieties of them. So in this case, we've built a small fleet of 3 linkages to sort of emulate the same situation where we have to not learn the tasks only for one setup, but actually for 3 times one setup. So we have 25 tasks on 3 similar but non-identical machines. Then going a bit more into the technical process of how we want to use this hot start, and what hot starting entails. So typically we have an operator or a user defining which task needs to be performed. We determine we want to do this task, so we have this combination of constraints, and then we want to apply it to the system. But of course, the question is then how can we find the best signal to use there? So we do not want to have a conservative control, we want to find the actual optimal control signal, and the question is how can we get there? Few classical options, relying on expertise, not always available. Using a physical model, also often done, closely related to like typical classical control theory. But of course, this is not trivial because typically the model is not linear, in this case especially because you have a rotation to translation motion. How should you get the model parameters? All of these things mean that neither the expert nor a model can get it right the first time around. So you will need a kind of fine-tuning process. So you have a first guess, then you try something, you learn, you go through a kind of a cycle, adjusting your control until you get a good result. This is both the case for experts and for like automated learning procedures. In this research, we've used mostly a model-based process to do this fine-tuning, which I'll show on the next slide. So here you will see trial after trial. The very first trial, it starts again. This red line, this is not good, not good, not good. And then gradually it converges to something that's actually respecting the bounds. And it's the minimal energy profile shown on the left. So this is actually quite useful. So it automatically finds the good controls, but it still takes, in this case, somewhere around 8 trials to get a good signal. If you imagine doing that for millions of tasks, this will still be very time consuming. So the question is then, can we do better than this? We could, of course, try to speed up the learning, but faster learning also means less robust and thus less safe learning. So the alternative that we'll study is to actually get the first iteration better. So we'll, instead of initializing based on expertise or a model, we'll do the hot starting. So that means that we'll get a better first guess for the very first signal to apply, hopefully thereby making the learning process as a whole much better. So in this case, we want to, for example, hot start this task on system 2. Hot starting would then mean that we look at the previous data, for example, system 1, the same task, system 2, a different task, and then combining that information somehow in a hot start to have a much better first guess for a signal to be applied. That was shown just for a single task. Of course, in the end, we want to do this in a kind of systematic way, where we have all possible tasks, many machines, where we keep and build a big database of tasks, where we hot start, then fine tune if needed. Probably it will still be needed to do some fine tuning, save the result, update the database, so that hot starting can be improved for future tasks as well. So hopefully in the end, this will bring it down to a full process of still some fine tuning, but much less than if we would not use a hot start. And also wherein the transients would be much better because the first initial guess would always be improved with respect to the current situation. Then I guess the core of the talk would be how can we do this? So it's all easy, of course, to say that we need to get a better first guess by combining all the previous information. We've looked in the past at doing this in model-based manners. In fact, we've gotten some very good results with that, but only in some cases. So in some other cases, it's just not possible to get good results. It's a bit inherent with model-based approaches. So if you don't have the right models or the data is not the right format, it's very difficult to generalize these methods. So sometimes they work, sometimes they don't. That's why I want to look at AI-based methods to have a bit of more of a generic approach. It would be easily extendable to more different conditions. We've looked at more or less 2 different methods to do so. So 2 AI-based hot starting solutions. 2 alternatives, one that we developed at Flanders Make, targeted at doing this problem. And then one other technique implemented by the VOB, or a group of Helsen, more or less doing the same problem within a different approach, a different solution, which will be shown to be complementary for different kinds of situations. And now I will give the word to Jan, who will explain a bit more on the different methods and then when you should use which of the 2 options.
Okay, thank you very much. Let's see if we can move to the next slide. Yes, so as mentioned, the goal is to start using AI methods to come up with a better first estimate for the controller settings and to do this in a more objective way based on experience from the past. And the advantage here is that we can use generic methodologies based on AI, where there is less fine-tuning required. So you don't have to have a fully updated simulation model or physics-based model of the system in order to be able to do this, which allows us to scale up to much more data types and more complex combinations of controller settings. What is also an advantage in this regard is that you become less and less subjective. So the algorithm will always work in a similar way, and it will converge from all of the knowledge. It's not the individual expert anymore, but it's the combination of all the experts together and all of the lessons learned from the past that are used to move ahead. So how is this practically done? First, we'll give an overview of the methodology as such, and then go into the specifics of the two methods that are proposed. So first, for each of the AI methods, there is always a training step. So in the training step, you need labeled data. This is data where you know whether the controller settings are good or bad, and whether they are violating the constraints or they are actually as they should be. The more data you have, the faster and better you can converge to a fully trained model. But of course, you need a lot of manual work because you need to have this labeled data set. So first you perform using the labeled data set an offline training step. This is computationally intensive and will take also quite some time. But then once you have the model, you can deploy it and you can use it to predict controller settings or suggest optimized controller settings, which then afterwards are fine-tuned as it was done before on the true specific context. The more things you've seen in the past, the better it goes. The first approach is the one proposed by Flanders Make, where a random forest regressor is used as the core of the AI model. It's a method that is easy to apply on a limited amount of data, where the labeled data set contains information, so an idea about the machine and controller settings that were set in the past. So there is this need for machine ID, as we'll follow later. Once the model is trained on the data that is available, albeit a limited or a big data set, doesn't matter, it's deployed for the first prediction of the control parameters, whereas afterwards you have again this fine-tuning step. For the VUB, okay, I pushed one too many. For the VUB approach, there is an additional concept here. So the model is based on a neural network approach, and it uses a burner run. So in essence, it uses a first iteration where controller settings are given and where a first run is done with the system in order to get an idea about how the system's dynamic response is. So you can see this burner run as a kind of dynamic identification of the machine. And then once this information is known, the model is used to give a better first guess and a faster convergence to the true optimal parameters. So what is different here? You have a labeled data set where you have good and bad controller settings for certain trajectories, but there is less detailed information necessary about the machine itself. So there is no ID of the machine required in order for the model to run. The difference is that you have this burner task where you first do a first iteration to do this kind of system identification step. To make the training faster, more reliable, and have more data, virtual data is used in addition. So a simulation model is used to generate a lot of trajectories and a lot of possible controller settings that is learned by the neural network and then used in the hot starting methodology afterwards. So if you compare the two methodologies, so the Flanders Make one has no burner run. It can build on a smaller data set, but it has the requirement of the machine ID. The VUB one has built on virtual data from a simulation model. And it can be reused efficiently when there are changes to the machine, because of this burner run that gives a kind of system identification step. Okay, so then let's go to the experimental part with Bruno. You are muted.
Okay, no, thanks. So the system that I actually showed before is a physical system that we've built in our lab in Lommel. So we got 3 of these linkages side by side. In this case, we'll build a demo on this setup where we will say 1, 2, 3 systems. Some of them are red, which means we have not yet learned the task. Some of them are green, which means that we have already found a good task set of control parameters. And then the goal now is to choose a new one, which is red, so not seen yet, and then to check how well it works if you want to start looking for an optimal control signal for this new task. First, we'll do this without any hot starting, just a classical approach, which is already using a model to avoid starting too poorly. It's not using a very advanced method for starting. So I'll press play. Now you will see the system moving quickly, slow motion replay, and the results gradually being added to the screen. You'll see that it starts poorly and gradually converges, like in the previous graphs, to a good result. One of the more important graphs is this one. This will show like the cost function, which is a combination of constraint violation and energy being used. So the lower this gets, the better of a solution that we have found. So as said before, it takes roughly 8 to 10 trials to get a good result, in this case without hot start. So we get there, but we start out poorly if we do not use a good first guess. Then we will do the same, but now we will use a hot start. So we've checked the box for AI-based hot start. So we'll use the previous information to train a hot starting algorithm to make a better suggestion for the first guess. But afterwards, we will keep using the same fine-tuning mechanism. So you will again see the system moving, gradually performing experiments, but you should mostly see that the first trial now is already much better than before. So and as a consequence, we are roughly at the level of the final performance after about 3 trials. Minor improvements are still being made, but it's also much faster and mostly also much better first guess, leading to, for example, less possibilities for damaging the system during the startup. Then one more thing we've looked at is what happens now if you want to apply this not for system 1 and 2, but for system 3, when you, for example, have not yet seen any data on system 3. So now we're essentially extrapolating to a new system. So we've only seen tasks on system 1 and 2. We want to hot start this one on system 3, which is slightly more difficult, of course, because there's less relevant data available. But then we'll train the model on these 2 systems and build in some robustness, and we'll see how it works. So we again start applying the method. The reference line is showing what happens if you don't apply hot start. So there's no animation for that one. But with the hot start, you will see that it now already starts much better, more or less at the same level after again 3 to 4 trials, compared to let's say 5 to 6 or so if you would not use a hot start. So again, showing that even for a new system which we have not seen before, applying this hot starting idea actually makes quite a lot of sense in improving the first trial performance when compared to classical methods such as a model-based solution that we used here. Okay, so this was more or less showing the performance, and then I think Jan will now give some conclusions about general applicability.
You're unmuted, Jan.
Same problem. So what you can see is that hot starting brings quite some advantage to the controller optimization. We've shown that it can handle some of the drawbacks of classical approaches. What is crucial in this regard is good training data. You need to build up experience from past iterations, which you can then leverage to be faster in the hot start. There, the training size is of course important, and it's important to have enough similarities so that the data is looking like the machine that you are actually now trying to hot start. It is definitely an advantage for commissioning phase, adapting to new conditions if you make changes to the machine or if you do upgrades to the machine. And it can help in making the controllers, in tuning the controllers and reducing the tuning time when there are bigger challenges ahead. For example, when transients are present and so on. We still have quite a trajectory to go in this case, but the results already look promising. In general, we've shown this on one example, but there is also potential for other industries and other examples within the manufacturing industry and beyond. So for example, for milling machines or other production machines, it can also be used linked to the previous, not previous, but the one before presentation on driving autonomous vehicles and doing optimized vehicle maneuvers, as well as driver profiling. You can use it to detect similarity in battery response in hybrid vehicles. And it's also interesting for wind farms, on which also a lot of data is available within the AI program, and where these methods are benchmarked to do optimal set point control, where for each machine in the farm, the set point is optimized based on the performance and the condition of the machine to meet a joint production goal. So in conclusion, the methods that we are using here were showcased on a particular example. We are moving ahead in this regard, but there's still a lot of untapped potential, and we are open for new collaborations in this regard. Right, thank you for your attention. Thank you.
Okay, thank you very much, both Bruno and Jan, for this nice presentation. So yeah, we still have 5 minutes at least for a Q&A session, but I see also a polling question. Maybe you can just quickly answer it, and then yeah, you can immediately raise your question or ask it directly to the presenters. I do not know if there are any questions or comments you would like to give about this webinar or about the topics. I saw maybe just to start some questions in the chat about speech, about AI-based speech networks, and the fact that yeah, it might be interesting to merge it in a bigger platform. So maybe Hugo or Quinten can give maybe an insight about this discussion, just to share it with the rest of the team.
Well, I kind of answered the question on in the chat already, unless there's a new question which I missed. So yeah, I mean in spoken language understanding, the task that you want to achieve is always, also if you use dialogue flow, is always application specific. You want to map speech onto an interpretation within your particular application. So there will always be an application specific aspect to what you're doing. Now, both the dialogue flow and what we offer are generic approaches that you can apply to many different applications. I mean, in a matter of half an hour or something, we prepare for this use case, and another half hour we do another one. Now, to make it, yeah, I mean, this in terms of platform, there's quite some differences, of course. I mean, Google is just omnipresent, and we are just a university somewhere. Yeah, I don't know if that answers the question. That answers the question.
Yeah, it was more indeed to give some insights, but indeed, if there are any comments about this, please go ahead and can have a live discussion about it now. But I see There are no questions raised so far in the chat, or nobody has question. Maybe also another one related to the presentation that's given by Picanol and the presentation given by Jan and Bruno later. I don't know, Patrick from Picanol, how do you do let's say, do you practice the hot starting today, or how do you do now the reconfiguration of the controller of your machines?
No, mostly we are using conservative controllers, so we have to specify the controller parameters in a conservative way so that it will work for all conditions that we will encounter. So no, real hot start is not yet done, but is indeed a good evolution to see in future of this can help us, of course. Yeah. But actually, we are not doing this yet.
Yes, and conservative controllers based on models or based on experts?
Based on expertise and lots of trial and errors and so on. Yeah, less based on models. Yeah, the weaving process is quite a challenge to get this modeled. So we don't have the models available for the weaving process, unfortunately.
Okay, good. So as I don't see any questions raised so far, and we are also 14:30, so this is the end time. I would like to thank you all, first of all, the presenters for preparing and giving this presentation today, and also to the attendees for your presence. And for your information, this webinar is part of a series of 3 webinars. So the next one is going to be given on the 20th of May, where we are going to speak about AI applied to systems in order to make a seamless communication with humans. So how can AI be used to support operators? That would be the topic in the next webinar on the 20th of May. So I wish to see you or to talk to you. That's from now to then. So thank you again for your presence, and yeah, talk to you then next time. Have a good day.